me turn on the recording. Yes. Welcome to the next lecture of Math 210, Intro to Differential Equations. In the previous lecture, we were discussing power series. So we discussed a couple of concepts of a power series. What is a power series? Power series is basically a series of the form summation n from 0 to infinity Cn x minus x naught power n. This is a power series, and we discussed what is the radius of convergence, or what is the interval of convergence of a power series. Interval of convergence, it was basically x minus x naught mod less than r, where r is the interval of convergence of the power series. And we also discussed how to check whether the given series is convergent or not. For that, what we do, we discussed ratio test in the previous lecture, ratio test. There are other tests, I told you, which you have, I think, already studied in your earlier classes, and in particular calculus courses. Ratio test was limit n goes to infinity Cn plus 1 divided by Cn mod. This limit, if this limit is finite, L, and we discussed three cases. When as L is less than 1, the series is convergent. When as L is greater than 1, the series is divergent. And when L is equal to 1, this test is inconclusive. It doesn't tell us about the convergence of the series. Then we have to use some other means to check the convergence of the series. We can apply some other tests to investigate about the convergence of the series. Now today we are going to discuss some other related concepts of the power series. For example, power series as functions. As functions. A function f of x can be defined as a power series. A function f of x can be defined as a power series. For example, f of x is equal to, we can express it in the form of a power series x minus x naught whole power n, or some different general term which involves the powers of x. For example, you might have studied already Maclaurin series or the Taylor series of functions. I hope you know what is the series form of this function, e raised power x. E raised power x is a function, and we can express it in the form of a power series. So this is nothing but summation n from 0 to infinity x raised power n divided by n factorial. So you can see that this is in fact a power series, n from 0 to infinity, 1 by n factorial and x minus 0 whole raised power n. You can match these two series that this is exactly the type of power series. In fact, this is the Maclaurin series. You have already studied how to find Maclaurin series or the Taylor series of a function. So this is in fact a special case, which is again the power series. So a function can also be expressed, any function can also be expressed in the form of a power series. Okay? Not all functions, but a great deal of functions can be expressed as the form of a power series. Now, many other examples are there of the functions which can be expressed as the power series. For example, we can also have a series of the sine x, cos x, many other functions. So any function can be expressed in the form of a power series, where the domain of the function is basically the interval of convergence of the power series. For example, what is the interval of convergence of this power series? It's the convergence interval of convergence of this power series is what? If x mod is less than 1. Okay. Then the domain of that function is also is the interval of convergence. Interval of convergence of this series is what? It is -1 to 1. So this will be the domain of that function, which can be expressed as the power series. There are other examples given in my notes. You can see them. Sin x can be expressed as a power series, cos x, and many other functions. Now, the important thing which we need to discuss here is that whether this function or the power series is differentiable or not, or whether the given power series is integrable or not on that interval of convergence. Yes, fortunately, we say that if r is greater than 0, r, what is this? R, it is the interval of, radius of convergence. If r is greater than 0, then f of x is continuous and differentiable. Continuous and differentiable function on the interval of convergence of the power series. On what interval? On x naught minus r, x naught plus r. What is this? This is basically the interval of convergence of that power series. Then we can obviously write f of x, or you can say y is equal to f of x is equal to power series y is equal n is equal to 0 to infinity cn x minus x naught whole power n. If this function is continuous and differentiable, then obviously we can take the derivative of the power series. And how to take the derivative of power series? We just write here f dash, and we take the term by term differentiation of the power series. In fact, how can we write it? If we open this summation, we can write c naught plus c1 x minus x naught whole power 1 plus c2 x minus x naught whole power 2 plus so on, and plus some ck or cn x minus x naught whole raised to power n plus so on. This is how we can open the power series, and by taking derivative of each term. This is called term by term differentiation of a power series. The first term is constant, its derivative is 0, plus second term, here we can take the derivative of x is 1 and x naught is 0. So it is c1 plus here the derivative 2 comes down here, and the derivative is 2c2 x minus x naught power 2 minus 1, which is 1. Okay, similarly, so on, plus cn, and the derivative of this thing is n times x minus x naught whole raised to power n minus 1, plus so on. If we sum up this series, here, notice that the first term is 0. So this series is now, it becomes, now n starts from 1. Previously, it was started from 0, but now in the derivative of this power series, the first term has become 0. So now the summation will start from 1 to infinity. C1, C2, and so on, Cn. And here you can see that here if we have 1, 2, and so on, n. So here we must have n, x minus x naught whole raised to power n minus 1. So this is basically the derivative of this power series. What we do, in fact, we take this n down here and then n minus 1, and the summation started from 1 to infinity. Similarly, when we take the second derivative, in the second derivative, another term would become 0. Another term, this term will also become 0. Let me add people trying to join in. Okay. Now, when we take the second derivative of this power series, the second term will become 0 again in the second derivative. Now the summation will start from 2. So y double dashed, it will be summation n from 2 to infinity n. And again, this n minus 1 will come down here and we'll have n minus 2 here. So n into n minus 1 Cn x minus x naught whole raised to power n minus 2. So this is the second derivative, and so on. Similarly, we can write the third derivative. In the third derivative, summation will start from 3 to infinity. Similarly, because the third term will be constant and it will become 0 when we take the derivative. And here we'll have n into n minus 1, n minus 2, Cn x minus x naught whole raised to power n minus 3. So this is how we can take the derivatives of a power series. I hope you get it. If you have any question, you can ask me. I hope you also got it, why we increase the summation index by successively taking the derivatives. In the first derivative, the first term in this series will become 0 and the summation will start from 1 to infinity. In the second derivative, the summation similarly will start from 2 to infinity. In third derivative, the summation will start from 3 to infinity, because each term, each first term will become 0 in the successive or in the subsequent derivative of the power series. I hope you get it. This is how we take the derivatives of a power series. If you have any question, you can ask me. If no, now how to integrate a particular power series? If again y is equal to f of x is can be expressed as a power series, which is summation n from 0 to infinity Cn x minus x naught whole raised to power n, then what we do, we take its term by term integration. So it becomes, if we open this thing, C naught plus C1 x minus x naught whole raised to power n, 1 plus C2 x minus x naught whole raised to power 2 plus so on plus Cn x minus x naught whole raised to power n plus so on. So what we do here, we take the integral of each term, integral of C naught with respect to x plus C1 integral of x minus x naught whole raised to power 1 dx plus C2 integral of x minus x naught whole raised to power 2 dx plus so on plus Cn integral of x minus x naught whole raised to power n dx plus so on. So when we take the derivative integral of this thing, here we have a C naught which comes out of this integral, and what do we get here? C naught x, x minus, in fact, in order to bring the uniformity, you can write here x minus x naught. Okay. Plus, here we have the x minus x naught whole raised to power 2 divided by 2 factorial. Sorry, divided by 2, not factorial. So similarly, plus C2 x minus x naught whole raised power 3 divided by 3 plus so on plus Cn x minus x naught whole raised power n plus 1 divided by n plus 1 plus so on. So if we sum up again this power series, what do we get here? Summation n from 0 to infinity, because we cannot have here a negative index and cannot start from -1 in the power series usually. So here we have when n is 0, here we have 1, and we have 2 here. Sorry, when here we have 1, we have 2 here, and so on. So we can write here Cn x minus x naught n plus 1 divided by n plus 1. So this is the power series after integrating each term. And this is called integration, term by term integration. Let me add other people. I hope you get it, how to write a power series, how to take its derivative, and how to take its integral. If you have any question, you can ask me.
एक चीज मुझे कंफ्यूजिंग लग रही है थोड़ी। हमने सी नॉट के अंदर x माइनस एक्स नॉट मल्टीप्लाई कर दिया है, तो और हम उसका जो इंटीग्रल ले रहे हैं वो x के रिस्पेक्टिव ले रहे हैं, तो x माइनस एक्स नॉट हम किस तरह मल्टीप्लाई कर रहे हैं?
देखिए x, अगर आप 1 का इंटीग्रल लें, 1 का इंटीग्रल, फॉर एग्जांपल 1 का इंटीग्रल आपने लेना है, ठीक है, तो इसका इंटीग्रल क्या होगा? x। हम इसको x प्लस सी भी तो लिखते हैं ना, कांस्टेंट ऑफ इंटीग्रेशन, ठीक है। Whenever we take the derivative of x plus c, it again becomes 1, because derivative of x is 1 and derivative of c is 0, ठीक है। And for our convenience, यहाँ पे x minus 1 का x minus x naught का derivative यहाँ पे क्या होगा? c naught comes goes outside and we have 1 here. अब 1 का इंटीग्रल x भी होता है और x minus x naught भी होगा, because x naught is some constant, ठीक है। And for our convenience, we can write here x minus x naught, because x minus x naught का derivative again क्या आ जाएगा? 1 आ जाएगा. To bring the uniformity in the power series, we write here x minus x naught so that we can write the nth term, or we can write this series in the sum form. ठीक है? क्यों महद? Are you clear?
Yes, sir.
Okay. Just for our convenience, we can write here, instead of x, we can write x minus x naught. Okay, to bring the uniformity in the series, because when you take the integral of some function, you have to add an arbitrary constant in that integral. Okay, because that constant might be 0 while taking the derivative. I hope you get it. Now let's come to the a theorem which gives us the existence of the power series solutions. बल्कि यहाँ पे ordinary and singular points. Now let's start applying this method, how to solve the differential equations by using power series method. Before starting, we need to discuss ordinaries and singular points of any differential equation. Okay. If we have a second order differential equation, consider this second order differential equation, a2 of x y double dash plus a1 of x y dash plus a naught of x y equal to 0. I told you that power series method, we shall apply this method in order to solve particularly second order homogeneous linear differential equation. We can apply this method for higher order differential equation, obviously, and other kind of differential equations, which have a particular kind of right-hand side, for example, polynomial functions. Then we can apply this method as well. Or at least the right-hand side function can also be expressed as a power series, as we discussed here, exponential of x and cosine of x, sine of x, they can be expressed in the form of a power series. In order to solve the non-homogeneous differential equations, the right-hand side function is also a sum function which can be expressed in the form of a power series. And while comparing the coefficients on both sides, we can see how to compare them while doing the solution. Now, again, we can solve higher order differential equation by using power series method, but we'll concentrate on the second order differential equation here. Now, what are the ordinary points of a second order differential equation? Number one, if a2 of x is not equal to, चलें पहले singular points कह लें. If a2 of x is equal to 0, for some value for some values of x, say a2 of x, maybe x ना कहें, कुछ और कह दें, a2 of x is equal to some b कह दें, x is equal to b. यहाँ पे मैंने क्या कहा हुआ है, हाँ, x naught कह दें, ठीक है. Say to x2 of x naught is 0, then x is equal to x naught is called is a singular point of the given ODE. These could be points as well. Okay, if this is a single point, then x is equal to x naught is a singular point of the given differential equation 1. This, if we call it 1, this is a singular point of ODE 1. Okay. Means if the coefficient of y double dash, is 0 at some point of x, then that point is called singular point. Otherwise, if a point is not a singular point, then it is called ordinary point. Okay? If a point x is equal to x naught is not a singular point, then it is called ordinary point of that differential equation. Ordinary point or points of ODE 1. Okay. For example, if we have an ODE of this form, x square minus maybe 9, y double dash plus x y dash plus maybe 9y is equal to 0. Then you can see here that the coefficient here of y double dash, which is a2 of x, is what? It is x square minus 9, and it is 0. If we put it equal to 0, we get what? X is equal to plus minus 3. So these 2 points, x is equal to 3 or minus 3, they are singular point of this differential equation. All other points, okay, all other points means other than plus 3 and minus 3, they are ordinary point of this differential equation. So these are singular points, and all other points except this, you can write it minus infinity to minus 3, union minus 3 to 3, union 3 to infinity. All these points are ordinary points. Ordinary points. I hope you get it. If you have any question, you can ask me. If the second order differential equation is basically the general form of the second order differential equation, we should know if the differential equation is in the standard form. For example, if we divide the a2 of x and get y double dash p of x y dash plus q of x y equal to 0. In this case, where p of x is what? P of x is a1 of x divided by a2 of x. Okay. And q of x is what? It is a naught of x divided by a2 of x. Then the points where p of x and q of x are not continuous, because these are fractional functions. Okay. So if the denominator of this p of x is equal to 0 at some point, then that point is called singular point. All other points, if you can say that if p of x is not continuous at x is equal to x naught, okay, then x equal to x naught is a singular point of the given differential equation. Okay. P of x, and you can say p of x, if p of x and q of x are not continuous at x equal to x naught. आप and कह सकते हैं और भी कह सकते हैं यहाँ पे, दोनों में से कोई एक भी हो, if either of these two functions or at least one of these two functions are not continuous at some point x equal to x naught, then we say that x equal to x naught is a singular point. For example, अगर आप उसमें the same differential equation, you divide all the differential equation with x square minus 9, you get 9 over x square minus 9 y equal to 0. Then you can see that here we have p of x and q of x. Okay. We can clearly see here that p of x is what? It is x over x square minus 9, and q of x is what? It is 9 over x square minus 9. So at x is equal to plus minus 3, because the denominator here is 0 at plus minus 3. Therefore, x plus minus 3, these are singular points. All other points are ordinary points. Okay. Now, the power series method is applicable only for the differential equations, and we can find the solution of these kind of differential equations around the ordinary points. Whenever we have a singular point in the differential equation, then and we want to find the power series solution about that singular point, then this method fails. Okay. For example, if you have a power series, if you assume that the solution is y and it can be expressed in the form of a power series x minus x naught whole raised power n. then this x naught should be ordinary point. Ordinary point. It should not be a singular point. Okay. Then we can apply the power series method. Once again, I'm repeating it. Any second order differential equation or any higher order differential equation, homogeneous and linear, it can be solved by using power series method. And we assume that y in the form of a power series, where x naught should be ordinary point of that differential equation. This is what we call it. This is a power series about x naught. About x naught means its interval of, this is basically the center of the interval of convergence of that power series. Okay. Then we can solve it. If it is the ordinary point of that differential equation, then we can solve that differential equation by using this method. If this is a singular point, then this method fails. Remember this. Okay. So when method is applicable, when power series method, power series method is applicable if x equal to x naught is ordinary point of given ODE. Okay. Second, not applicable if x equal to x naught is singular point. Singular point of given ODE. When x equal to x naught is the singular point, then we have to modify that series. And that is called a probinus series, and we'll discuss it after discussing the power series method. We have to made some adjustment in this power series. We have to make some adjustment in this power series in order to use, you can say that an advanced version of our series method, which we call probinus series, in order to solve the differential equations using series method. I hope you get it. If you have any question, you can ask me. Now, there is a theorem here which we need to discuss. Existence of a power series solution. When the method is applicable, and now we are going to discuss if the method is applicable, what is the criteria for the existence of the power series method, power series solution, in fact. You can see, you can have a look at the concepts which we have just discussed. Let me clean the board and then we'll restart. Kindly mute your mic if you don't have any questions. So a theorem, which is basically the existence of power series solution. The theorem states that if x equal to x naught is an ordinary point, of the ODE, ODE1, which we have written there, which is A2 of x y double dash plus A1 of x y dash plus A naught of x y equal to 0. We can always, if this is the ordinary point of this differential equation, okay, we can always find two linearly independent solutions power series solutions. In fact, independent solutions in the form of a power series centered at origin, centered at x equal to x naught. That is, the power series solutions are basically of the form y of x is equal to summation n from 0 to infinity cn x minus x naught whole raised power n. Both solutions will be of this form, in the form of a power series. This series converges at least on some interval x minus x naught mod less than r, where r is the distance from x naught to the closest singular point of the ODE, obviously. Now, what does this theorem tells us? That any second order differential equation, it can be solved around any ordinary point x equal to x naught. X equal to x naught is an ordinary point of this differential equation. Then we can always find two linearly independent power series solutions. Why it is important to find two linearly independent solutions? Because the order of the differential equation is 2. So we must have two linearly independent solutions in order to write the general solution of this differential equation. Okay, and I hope you know how to write the general solution of second order differential equation. It should be a two parameter family of solutions which involves two arbitrary constants. So and this series converges in the interval x minus x naught, where r is the distance, r is basically the radius of convergence of that power series, and the distance of r from x naught is minimum, or at least is basically, it is the closest, r is the distance from x naught to the closest singular point. For example, we discussed an example on this board, on board 2, this one. Okay. For example, this one, look at this example. Here we have plus minus 3 are the singular points. Now, if we try to solve a power series solution, if we try to solve this differential equation using power series method around the point x equal to 0, for example, around the point x equal to 0, where x equal to 0 is the singular point of this differential equation, then we must get two power series solutions of this differential equation, where the interval of convergence must be what? Of both those power series, that should be x minus 0 less than 3. Okay. Why this is 3? Because if we take the ordinary point as x equal to 0, then the interval of convergence should be from 0 to the closest singular point. The closest singular point is either plus 3 or minus 3. So you can take plus 3 here. You can also take the minus 3, but you have to put a greater than sign there. But here, radius of convergence is always basically, you can take it positive, because हमने डिस्कस किया था कि डेरिवेटिव्स किसी भी पावर सीरीज के कब एग्जिस्ट करते हैं, कॉन्टिन्यूस कब होता है, when if r is greater than 0 then the function is continuous and differentiable. So we choose here 3 as r. So this must be the interval of convergence of this the power series solutions of this differential equation. This theorem tells us this thing. If you have any question, you can ask me. So let's repeat it. If x equal to x naught is an ordinary point of the given differential equation of this form, then we can always find two linearly independent solutions and centered, basically two linearly independent solutions in the form of power series centered at x equal to x naught. Where x naught is an ordinary point. And we can find solutions in this form. And this series must have an interval of convergence of this form x minus x naught less than r, where r is the distance from x naught to the closest singular point. I hope you get it. I have tried to explain you with the help of example as well. We'll discuss this further when we solve differential equations using this method. If you have any question, you can ask me. Next, one thing which is very important to discuss is basically how to add two power series. Or we shall discuss this while solving an example. And also, I shall also explain you how to, what is the idea behind solving the differential equation using this method. For example, let us solve this differential equation by using power series method. Solve the following ODE by using power series method about or around the ordinary point x equal to 0. So the differential equation is y double dash plus xy equal to 0. And we need to solve this differential equation about x equal to 0, where x equal to 0 is the ordinary point around which we need to solve this differential equation. Okay. The idea behind this method is what? We assume that that y of x is equal to summation n from 0 to infinity cn x minus x naught is what? It is 0. X naught is 0 here. So we assume that this is a power series solution of this differential equation where cn are unknown constants. Okay. In fact, in this method, we assume the solution is of this form. And by inserting this power series into the differential equation, we try to find these unknown constants, where Cn are unknown parameters or constants, you can say, unknown constants. Okay. The purpose here is to find the values of these constants. In order to find these constants, what we do, we put this series here in this differential equation. For example, if we call it 1 and we call it 2. Okay. And now what we do, we take the derivatives of this power series. How many derivatives do we need? We need 2 derivatives. So what is the first derivative? It is summation n from 1 to infinity n into cn x power n minus 1. And the second derivative must be summation n from 2 to infinity n into n minus 1 cn x power n minus 1. I hope you know why I have written here in the derivative n from 1 to infinity. Y double dash n from 2 to infinity. Because when we take one derivative, the summation moves forward to 1. In the second derivative, we write n from 2 to infinity. I have already explained it. I hope you know that.
सर
जी बेटा.
x पावर n minus 2 नहीं होगा सेकंड डेरिवेटिव में?
कहाँ पे? यहाँ पे?
Yes, sir.
तो 2 ही लिखा हुआ है ना, गौर से देखें. So now what we do, we insert second derivative, first derivative, and y here. Here we don't have y dash, so we don't need to put y dash. So we can only put y double dash and y here. So y double dash क्या आएगा? N from 2 to infinity, n into n minus 1 cn x raised power n minus 2 plus x times y. So y is n from 0 to infinity. Cn x power n is equal to 0. Okay. So we obtain two power series here. Now, what we have to do here, we have to take common summation term, and we also have to take common the term which involve x. And why do we do this? I'll explain you later on. अब देखिए यहाँ पे summation is starting from 2 to infinity. But whenever we put n is equal to 0, this term becomes 0. Whenever we put n is equal to 1, here we have 1 minus 1. Again, this term becomes 0. So, yes, is there any question? It's 12:50. I shall start the next lecture exactly from here. Okay, remember this thing. And now you can start the quiz. Okay, if you have any question, you can ask me, and after that, you can start the quiz.